By the way, Nati, you go to office pretty early.
Yeah, I usually wake up early. So 9 a.m. is the middle of the day for me.
Oh, by the way, Ethan, have you shared the screen?
No, you want me to?
Yeah, go. Please do.
Yeah. Okay. Let me get rid of this. Should I start?
Not yet. Okay.
Not yet.
Not yet. So let me press recording. Wait a second. Oh, I see. For some reason, sorry. Something's wrong. Not sure. Okay, welcome everyone. Welcome to Harvard CMSA Quantum Matter in Math Physics seminar. We are delighted to have Ethan Lake speaking about his recent work. Ethan Lake right now is at MIT. We'll hold a speaker dinner for him at some point, and maybe today or tomorrow we'll clarify. If you have interest, please send me an email. And he'll be speaking about his recent work on dipolar Bose-Hubbard model, and there are two works and maybe more in the future. So let's pay attention on his talk and ask questions, interact with Ethan. It's all yours.
Okay, thank you, Juven. Yeah, and thank you everyone for getting up early if you're in America. I guess it's no problem for Natty, but for the rest of us, sometimes it can be a bit difficult. Let me also start by saying that I got kind of sick over the weekend, and I'm still feeling kind of brain dead. So you're not really going to get me at my best, but I'll try to make do. Okay, so sorry. All right. So before do anything else, let me thank the people that this work was done with. So the talk is kind of going to be split into 2 or 3 parts, and the first part is going to be some older work from early this year with Mike Hermele and Senthil, and then the second half is going to be about some pretty recent work with Senthil and Jung-Hoon Han and Hyun Lee from Korea. And then there will also be some upcoming work that I'll talk about briefly. And I should also point out that this most recent paper we posted here actually has a lot of overlap with something that was posted last Thursday by these authors, who also, well, I'll tell you exactly what we study in a sec. The good thing is that we basically, that both of our groups essentially agree on all the physics. There is one significant difference, though, which is that while we both did DMRG, their DMRG is, I would say, much more beautiful than ours. They really pushed the numerics a lot farther than we did in terms of resources. So I would definitely encourage people to check out this paper if they are interested in. Okay, so here's my philosophical motivation slide, right? So this talk, there are a few ways of approaching the kind of stuff that I'll be talking about in this talk, but kind of the way that I've been coming at things is the following. So, basically the big theme of quantum matter research, i.e. the study of, what matter does at 0 temperature when quantum effects are important, is really kind of governed by this fact, the undergrad fact that there's, all matter has both wave-like and particle-like properties, right? And, a lot of interesting things happen when neither the wave-like nor particle-like limit is really appropriate, right? And a lot of quantum matter research is all about like what happens when these two properties of matter compete with each other, right? Or an alternative way of saying that is just, how does kinetic energy, which likes to delocalize things, usually compete with interactions, which usually like to localize things? And a very
Excuse me.
kind of
Yes, in that case, can I just say you have two non-commuting operators, maybe order or disorder operator, they both interplay in the phases. That's what you
so
want.
we quantum mechanics has this uncertainty principle, right? And so things become interesting when the uncertainty principle is kind of like can't be ignored and determines how matter organizes itself at low temperature, right? So
Thanks.
I've chose to focus on position and momentum because that's usually what is going on in these kind of matter systems. And so a very kind of fruitful line of research is to like explore what happens when you can kind of tune the way in which this competition goes down by hand, right? So you can come in and qualitatively modify one or the other of this particle-like property or the wave-like property, right? So examples of that in condensed matter, there are a lot, and they're usually some of the most interesting things to study. So one example, from recent years is you can come up with materials where you just engineer the kinetic energy to be anomalously weak, right? So you can take, for example, you can take two sheets of graphene and stack them on top of each other and do some twisting, and they produce a system with very, very low kinetic energy, right? Another example is the quantum Hall effect, right? So in the quantum Hall effect, we turn on this gigantic magnetic field, and the electrons in the system get kind of localized to these cyclotron orbits, right? So you're kind of freezing, you're kind of quenching the kinetic energy. You're not completely removing it, right? There's still lots of stuff that goes on in the lowest Landau level, but you're kind of modifying the way in which kinetic energy can operate, right? You're making things non-commutative and so on and so forth, right? And so these two examples have gotten us quite a lot in terms of learning new things about quantum matter. Okay, in addition to these examples of a particular nice way of modifying this kinetic energy versus interaction competition is to, which is what we're going to be focusing on today, is to add a conservation law that quenches the kinetic energy in some way. And to that end, this talk is going to be about systems which have such a conservation law. So we're going to talk about, in this talk, we're just going to be focused on bosons, but you could think about fermions as well. But we're going to have systems of these particles with two conservation laws. So one is just going to be the conservation of the total number of particles. So this is the number of particles at site R, and I'm summing over R. And we're also going to add an additional conservation law, which is dipole moment conservation, which is the charge weighted by a certain component of the position, right? Okay, so maybe for the next couple of slides, let's just take this conservation law as like God-given, and I'll kind of motivate it further in a moment. Okay. So here are the rules of the game when we have dipole conservation, right? Well, I told you we also have total particle number conservation. So one rule of the game is that I can't just particles can't just be created and destroyed for free, right? I have to respect total particle number conservation. That's one rule of the game. Dipole does imposes some interesting things. So one is that if I have a particle just sitting here by itself, so this red guy is a particle, and then the white dots are meant to indicate empty lattice sites. This guy is totally frozen, right? He can't move because if it tries to move in one direction, you're going to change this dipole moment, right? So single particles are totally frozen. However, pairs of particles or groups of particles are actually not frozen, and they can indeed kind of push off of each other and move in opposite directions. So you notice that this process whereby these two particles move in opposite directions conserves the dipole moment. Okay. But of course, they can push off each other once they get far enough away. This pushing off is going to freeze out, at least if the interactions are local, and they'll be become stuck, right? So it's this kind of dynamics which kind of renders the particle motion glassy in some sense. And this was indeed the original motivation for one of the original motivations for studying these models and their connection with fractons and glassy dynamics and things like that. Okay, so that's this. But there's also an interesting thing is that in this system you can have a bound state of a particle in whole can actually move for free. So let's imagine now we have some background density of particles, and I'll use this blue dot to denote a hole, so an absence of a particle, and this red to denote, again, a particle on top of the background density. Well, this object here, this has, number -1, and this carries number +1. And so this object as a whole is neutral, and as a result, it can move without changing this dipole moment. It could just move for free. So individual particles are kind of localized, are kind of their motion is constrained, but these dipole objects can move for free. Okay, so these are the rules of the game. Okay, so there's been tons of work actually on the dynamics of dipole conserving systems recently. So by what I mean by this is, like, people will look at some, say, random unitary circuit which preserves dipole conservation, or they'll look at how a dipole conserving model thermalizes or doesn't thermalize. They'll study hydrodynamics and what happens when following quantum quenches in these systems. As you can imagine, these questions are very interesting because this kind of restricted particle motion affects how you're going to kind of transport information and thermalize and stuff like that, right? But there's been comparatively less attention devoted to like ground state phase diagrams, this kind of equilibrium physics stuff. Although see work of people below as a partial list of studies on equilibrium things. But this is also an interesting, equilibrium stuff is also actually interesting because this dipole conservation law qualitatively affects this particle versus wave competition that we were talking about a few slides ago, right? Because when you look at these hopping processes, right, if we call the processes which hop bosons, we call this like the kinetic energy. Well, the kinetic energy in these systems is basically intrinsically nonlinear, right? Because the motion of particles, while allowed, depends on their environment, right? It depends on what kind of other particles are nearby them. So in order for anything to move, it has to do so in a correlated way. And this, is kind of not something that we're used to thinking about. Okay, so the talk is going to be kind of about understanding how this works in a simple model system. Okay, so here's the outline. So I'm going to talk about first. I wasn't sure what kind of the background of people that would show up to this talk are. So I have the first part of this is I'm going to talk about a model that we've been studying recently, which is called this dipole Bose-Hubbard model. I'll kind of briefly explain what the phase diagram of this model looks like. And then the second 2 points are on some more recent work where we've done a more detailed numerical study of the model in 1D and found some interesting things. And then at the end, I'll talk about, even though I just said that I'm mostly interested in equilibrium physics, we kind of realized that there was some dynamical phenomena that we couldn't avoid. We basically have no choice but to do with, that are actually pretty interesting. I'll talk about that at the end. Okay, any questions before I get started?
Well, maybe let me just make sure. Earlier, when you say kinetic energy is nonlinear, is respect to what is nonlinear?
Oh, I just mean that, nonlinear in the sense of interacting, right? So, if you think about, say, this process, right? We're moving bosons around, but I can only move this boson if I also move this boson at the same time, right? So nonlinear in the sense of any process which implements boson motion, for example, can't be done with just a two boson creation or annihilation operators, right? You'll see that in
I understand. So you mean the kinetic energy is not a linear combination of a sum of the individual particles. There are some constraints.
Yeah. Let's talk about that on this slide. So here's the model that we're going to be focusing on. So this is basically the Bose-Hubbard model, except it conserves dipole moment. So Bose-Hubbard model, recall, is this model where you have bosons that are hopping on a square lattice, and they have some Hubbard repulsion, so they don't like to be at the same site. Maybe there's a chemical potential which sets how many bosons there are. And then the normal Bose-Hubbard model would have just like a term which hops bosons from one site to another, which is the kinetic energy term. Right? Here, as I was saying, that process is not allowed because of this conservation law. Instead, you have things like this, where I take these two particles on one site and they hop in opposite directions. That's exactly what this term here does, right? And when I was saying that the kinetic energy is sort of intrinsically nonlinear, well, you just look at this and okay, I have 4 boson operators, right? So it's unclear whether you should think of this as interactions or kinetic energy, right? Kind of a little bit of both. Some intuition for what this model is going to do can be obtained by looking at this first term here and realizing that it's actually just a single particle hopping term for dipoles. Okay, so let's come down here and let's define this operator which creates a dipole as the following. So we're going to create a boson at site I and destroy one at site I+1. So this is exactly this, I was showing this bound state here of the hole and the particle. That's exactly the kind of thing which is destroyed by this operator. And you can rewrite this hopping term here, this nonlinear guy, in turn is like this. So I have it's really just hops a dipole from one side to another, right? So the kinetic energy, this quote kinetic energy term, it kind of has a simple interpretation in terms of these dipole operators, while the interactions over here do not, right? So I definitely don't want to write this number operator in terms of dipoles. That would be horrible, right? Okay, so this is the Hamiltonian we're going to study. Let me just point out a few realizations, physical realizations, right?
Excuse me.
Yeah.
Is the potential term, should you consider instead the n times n minus 1 or just n squared?
Oh, yeah, sure. So if the usual thing is to write n times n minus 1, that just shifts your definition of this chemical.
Yeah, fine.
In fact, probably in the paper, I probably wrote it with the n minus 1.
Okay, thanks.
Okay, so I have 2 slides or actually 3 slides on realizations, where this comes from, right? So far I just said, let's just assume we have this conservation law. Okay, well, why would we expect something like that to be realizable in the real world? Well, one realization is in terms of strongly tilted optical lattices. So we have an optical lattice that's this like black potential here, and it's loaded with bosons and they can hop around. And the lattice is tilted, so meaning that subsequent sites have a potential which differs by some amount v. And I'm going to want to take this tilt to be very big, so much bigger than the u or the t, right? Okay, so why does this give you dipole conservation? Well, it's pretty simple. Basically, when this system is very well isolated from its environment, it conserves energy. It can't dissipate energy. And if this scale v is big, then if I try to hop a boson from one site to another, that boson is either going to gain or lose a very, very large amount of energy given by this v. But since the system is conserving energy, it has to kind of find some way of dissipating that energy into other parts of the system, which is basically impossible to do if this v is much larger than the other scales in the problem. So it turns out that actually in this scenario, you get an effectively dipole conserving model because, while these processes are not allowed, I can take bosons and hop them in opposite directions at the same time. And one will gain energy v, one will lose energy v, and that's net zero energy cost. So yeah, so this is one example. And in fact,
have a question.
yeah, go. Oh.
Do you still have the particle hole bound state being able to move in this tilted potential?
Yeah, that's right. Yeah, you do. So the
Well,
particle
like
hole bound state, right, is kind of like so the energy of this tilt potential just cares about like the number of particles, right? So if the net number of my if the net particle number of my object is 0, then I can move it for free.
Okay, thanks.
That makes sense.
Question.
Yeah.
Using some similar strategy, can I create some potential to realize something that conserves some higher multiple?
Yeah, I think that's possible. I think if you wanted to do quadrupole moment conservation, for example, in 2D, then yeah, perhaps you would need some like actually I'm not totally sure what you would need. Yeah, maybe it needs, I mean, probably needs to be nonlinear in some way. Yeah, I'm not sure exactly what the potential is, but probably. I mean, you can just add it if you just add a term here, which is some potential which depends on like say I times j or something, where I and j are two different directions.
Yeah. So this term is essentially v times the total dipole moment.
That's right. So just add this times the
large.
moment.
If v is large, it means the dipole moment is conserved. So if I just add to the Hamiltonian a big coefficient multiplied by the some say quadrupole moment, I think it's natural that the quadrupole moment will be conserved.
Yeah, I agree. So I guess that's going to look like something that you know has yeah, okay, so it'll be just quadratic. You have to have some quadratic potential. Yeah, that's right.
Thanks.
Yeah, and so we had to be honest, I haven't thought about that, but yeah, maybe kind of fun to do so. Yeah, cool. So with regards to this kind of linearly tilted lattice, there are actually some experiments that have been done on these kinds of systems. They're not exactly the model that we want. In particular, they study Fermi-Hubbard models, and they're really interested in kind of dynamical questions. But they're still very interesting, and I find the experiments super awesome. So one is by Emmanuel Bloch's group, and one is by this Princeton team. And yeah, I guess I won't explain exactly what these plots mean unless people are very interested, but they're basically studying some kind of quantum quench kind of deal and seeing how dipole symmetry affects the ability of these particles to kind of constrains their ability to diffuse. Anyway, I just bring this up to say that, you know, there are people looking at these kinds of questions in the lab, and it doesn't seem crazy to realize these kind of systems that I'll be talking about in the lab. And another example, which I won't really touch on too much, is actually the quantum Hall physics. This is just kind of an interesting observation that if you're in the lowest Landau level, you're really in you should kind of think about the lowest Landau level as a one-dimensional system with dipole moment conservation. And just to go through this real fast, you know, what you would do is in the lowest Landau level, you'd work on the Landau gauge. Say all your wave functions are extended along this direction. The x coordinate here of these wave functions, of course, is the identified with their momentum on the y direction in this Landau gauge. And momentum, what this ends up meaning is that momentum conservation in the y direction translates to dipole moment conservation in the x direction. And so indeed, you can map these say bosons in the lowest Landau level into a dipole moment conserving problem in one dimension. And yeah, maybe I'll come back to this very briefly at the end, but just to say that this kind of the quantum Hall system can actually be interpreted as a very specific type of dipole conserving model. Okay, so okay, those are some motivations. Now I'm going to tell you what the phase diagram of this model looks like. I'll
sorry.
mention. Yeah.
Can you explain what you just say? The dipole hopping becomes short range at the thin torus limit.
Oh yeah, I can. Yes, sorry, I think I was going over this too fast. So, basically what happens is that right, so we understand the dipole hopping, right? So if since these different strips are labeled by the ky momentum, if I want to conserve ky, then I have to conserve dipole moment. Now what sets the range of the hopping here between these different these Landau gauge wave functions, this hopping is kind of set by the spread, the amount to which these neighboring wave functions overlap. Now, if I have a thermodynamically large torus, then all of these wave functions are kind of right on top of each other, and the sort of range of the hopping is going to be very large in this effective 1D model. Sort of just because the linear dimension of this torus is, say, L, but the number of Landau gauge wave functions is L squared, right? That's the degeneracy. So the spacing in between adjacent sites is like 1 over L, right? So what that means is your effective hopping becomes very big. However, if I make this direction here of the torus small, then it actually the hopping becomes more short ranged, because then the number of Landau gauge wave functions is almost equal to the linear, it scales almost with the linear size of the torus. So people have done this before, where they've done like numerical studies of the quantum Hall effect on a thin torus, and then they've used this like effective dipole conserving model to kind of study that. And they've argued that like the kind of big torus is adiabatically connected to the thin torus, and have studied things like this. But I won't go into too much detail about that side of the story. But I can explain more later if you're interested.
Okay, thanks.
Yeah.
Just make sure.
Okay,
so
we're
make sure. I guess this probably just to clarify. So the dipole moment in X is related to momentum in Y, because there's a relation between the constraint between the momentum, maybe ky, and also the linear gauge potential.
Yeah, that's right. Yeah.
That's what
Yeah. So if I have a boson on this strip, it has momentum ky. Well, a boson on this strip to the left has momentum, say, k minus 1 in units of 2 pi over L, right? And this guy has momentum ky plus 1. So if I want to conserve momentum, I can't just hop a single boson, because that will kind of increase the y momentum of the system by 1. So I have to hop bosons in opposite directions in order to conserve ky momentum.
Okay, yeah. But let me just make sure, since you get here. So for the quantum Hall state, are you consider bosonic quantum Hall or fermionic? Usually it's fermionic.
Yeah, you can do both of them will map to a dipole conserving system. Yeah, so you could do either. Since most of the talk is about bosons, well, you can imagine bosons, but it doesn't really matter.
But quantum Hall here are incompressible, is that right?
Yeah. So you can have if your bosons are interacting, you can study
repulsion. Sure. But I say that if you have also superfluid phase, I suppose that's compressible. So it's certain phase only realized in this system. Maybe.
Yeah, that's right. So this quantum Hall reduction, it gives you a particular I'm kind of most of the talk is about like, let's just explore a big phase diagram in a big kind of parameter space where I can tune a bunch of coefficients and see how this dipole model does different things. In the quantum Hall problem, you basically just get one dipole model where everything, the Hubbard U and the hopping and everything is just set by the interaction projected into the lowest Landau level. So you're kind of just in one point of parameter space. So it's a little bit like maybe perhaps less interesting. Well, I mean, it's very interesting. There's a lot of rich phenomenology, but you're kind of the interaction is just kind of setting everything. It's not very tunable.
Okay, so it's like this type of phases you can now explore maybe superfluid type of
right. Yeah. So I mean, one thing you can do is to imagine, taking your favorite quantum Hall phenomenon, I don't know, the Pfaffian, bosonic Pfaffian or whatever, and then seeing, well, that must have some avatar in this dipole conserving model, right? So what does it mean? How do you get this 1D dipole model that like secretly has this Pfaffian inside of it, right? What is that? So you can explore those questions if you want. But we haven't done so.
Okay, maybe you can point out which type of phase it will be in the phase diagram if you point out this dipole Bose-Hubbard model later.
Yeah. So
yeah, let's go.
Maybe we can talk more about that later offline, because it's not totally. yeah, it's not completely trivial to see how that works, but yeah. Yeah, but thanks for the question. So, okay, so I'm just going to explain how we get this phase diagram. Well, it's very simple. You know, the first thing to do when you study a model like this, right, is to just do mean field theory, right? So I told you that these dipole objects, right, this particle hole bound state, these are the things which condense. Well, sorry, these are the things who can move around for free in the system. Single bosons are constrained, but dipoles can move around. And so the most natural thing to do is to say, well, when I increase T, well, the system is going to lower its kinetic energy by basically forming a Bose-Einstein condensate of these dipole objects, right? So the most natural thing to do. And technically, of course, it's very straightforward. You just basically just make this realization that dipoles are how the system is going to lower its kinetic energy, and then you just follow chapter 9 of Sachdev, right? It's a very standard analysis, and I'll just sketch what this analysis leads to. So here, you know, I'm comparing the phase diagram of the model we're studying, which is on the right, to the normal Bose-Hubbard model, which is on the left. Normal Bose-Hubbard model, remember, is just the model we're studying, except you have a single boson hopping term, right? And for the dipole Bose-Hubbard model, you have this correlated hopping. For the normal Bose-Hubbard model, here's what the phase diagram looks like. So this is as a function of chemical potential and hopping strength. Now, at low hopping strength, you have these Mott insulators, right? Where here in these orange regions, you have very weak kinetic energy, and the particles just basically sit on sites, and they're localized and they're insulating. Not much interesting is going on. But then when you increase the hopping strength, you form a superfluid. So this is gapless, has this, you know, field theory that everyone knows about. Okay, that's the story over here. What the story is on the right-hand side is what I'm going to explain in the next few slides. Okay, so here's the phase diagram. So the easiest thing to understand here is that we again have these Mott insulators where the bosons are just frozen at very small t, right? So if I just turn t, if I set the hopping term to 0, then these two models are exactly the same. So this dipole conserving model is also just going to give you these Mott insulators at small t. But then there are some other things here. In particular, there's this dipole condensate here in these green domes. I'll explain what that is in a sec. And there's also this what we're calling the Bose-Einstein insulator, which is I'll also explain in a sec. Okay, so here's how you should think about this phase diagram.
Oh, by the way, sorry to interrupt you. I just want to be detailed a bit, because your U and Subir's U, your mu and Subir's mu might be different by 1, or maybe different by U, a constant U, because the way you define the potential somehow is U times the number square instead of
that's correct. So I can
a unit of U or something.
That's right. So you'll note that I did not put any numbers on this y-axis, right? So regardless of what my convention is, this phase diagram makes sense. I didn't put any numbers. Yeah.
I think mu will shift by mu plus U in your convention. Anyway, yeah. Okay.
Yeah.
Right. Thanks.
Yeah. So we have these Mott insulators, and then we have these other things. So the kind of physics of the model can be understood by imagining that you tune across this red arrow. So you start in a Mott insulator, and you increase the strength of this dipole hopping, right? Well, you know, like we were saying, the easiest way for the system to lower its kinetic energy is to condense these dipoles. So that's indeed what happens in this green region. So this dipole condensate, this green region has a condensate of these dipole bound states. And then basically what happens is once you've condensed dipoles, that kind of unlocks the single particles to be able to move. So they can't move by themselves because of this dipole conservation law. But once we're in this dipole condensate, you can kind of imagine that we have these dipole bound states are sort of free. We can create or destroy them at will. And we can kind of hop a single particle effectively by just kind of fusing it with one of these dipoles in the condensate. And this kind of opens the door for single particles to condense as well, to form a to form a Bose-Einstein condensate of single particles, and that's what happens in this blue region. Okay, so yeah, I think maybe I'm not going to go into too much detail unless people are interested in, but in these phases, you can study the phenomenology of this phase where you have these dipole things condensed. Yeah, maybe you can, if people want to know more, just ask me, but I'm gonna otherwise I'm gonna go on to the next slide.
How about you explain? You have a time.
Okay, yeah. Well, I just don't want to bore people to death, but yeah. Okay. So, good. So okay. Here's what the dipole condensate is. So we said it's this superfluid of dipoles, but in the dipole condensate, the single bosons remain gapped, right? Just as in the Mott insulator. So if you just look at what happens with respect to the charge, like the objects which are charged carry non-zero boson number, this dipole condensate kind of looks like the Mott insulator. The individual bosons are gapped. It's incompressible, right? Meaning that you vary the chemical potential, and the density doesn't respond. It's insulating, so you can't, just meaning that like the boson number current, the conductivity of the bosons vanishes. And it's kind of described by a field theory that looks like this. So it looks like essentially your normal kind of superfluid. This theta vector here is essentially it's a vector where the indices run over this different spatial directions, and it looks like this. So I have this operator b dagger I and b I plus a, where a is x, y, z, whatever, a spatial direction. Becomes in the IR, it becomes this the exponential of this field theta. So this is kind of like the phase of the 8th component of the dipole condensate. So you have this simple kind of quadratic action which describes this region of parameter space, and that's basically the story with this dipole condensate. Superfluid dipole. Yeah.
Can I think of the dipole condensate phase as like a U1 dipole symmetry spontaneously breaking phase, and then
that's right.
A is the Goldstone modes?
Yeah, that's correct. Yeah.
Okay, thanks.
Yep. So we've kind of spontaneously broken this dipole symmetry, and we have this sort of Goldstone. But in the IR theory, we kind of like perhaps we can't really see that it's a dipole symmetry in some sense, in that, like, the IR theory, you just see this field theta, and it's just okay. We just have some XY models, right? But that's it, right? So you don't
I guess
see
like the number of Goldstone bosons is different than a normal U1 symmetry.
Yeah, that's just because you have multiple components of the dipole symmetry, right? So I have like the dipole moment along X and along Y and along Z, and each of those there can be some kind of phase twist for each of those order parameters.
All right, thank you.
No problem.
The original Bose-Hubbard phase diagram is kind of analytic, maybe at least at some mean field sense, right?
Yeah.
So how is your phase diagram? Is also analytic?
Yeah, basically that. So these two phase diagrams were obtained in the same way. Now, so caveats to this, right? So this phase diagram is morally correct. Why is it not exactly correct? Well, one thing is that in one dimension, mean field theory is not really going to capture things totally well, right? So that's part of the story. That's part of one of the things I'll talk about later in the talk, is what happens in one dimension. Another part is that there are some subtleties about what exactly happens at the boundaries between different Mott insulators and different phases. So like along this wiggly line here, and along this wiggly line, things like this. What happens here is kind of more dependent on the details of your Hamiltonian. There can be various like crystalline phases that occur here, and it's a little bit more complicated. So I'm sweeping some things under the rug, But this is sort of the qualitatively correct picture. Just as this is sort of the qualitatively correct picture of the regular Bose-Hubbard model. Yeah, Nadi.
Yeah, so at the two ends of small t or large t, you can expand the Hamiltonian, so one term dominates over the other. And
Right.
I think I understand that. But in the green regions, the
Right.
dipole condensate, all the terms are equally important. So when
Yeah,
you
that's right.
wrote the Hamiltonian the way you did, and you wrote some continuum description, is there some parameter that is taken to infinity to justify all the terms that you neglect?
Mhm.
Is it just going to low energy, or what? You need some parameter to justify the terms that you throw away.
Right. That's correct. So I think the small parameter in this regime is sort of the strength of the dipole condensate in some sense. So by what I mean by that is that when you're working in mean field, you know, you can kind of what you do in mean field is to replace part of this object, so the b dagger I minus 1 bi, you would in mean field you would replace one of those guys by just the expectation value of that operator, right? So this term here in the dipole condensate within mean field, you would replace this term basically by expectation value of this dipole operator times bi plus 1 dagger plus hc, right? Now when the expectation value of that object is small, you basically have a small effective single particle hopping, and you basically get back to this regular Bose-Hubbard model, right? So if I just replace two of these operators with their small expectation value, then I get back to this a model which kind of looks like this in mean field. And then that's kind of why these dipole condensate regions have the same shape as these regions in the superfluid, sorry, in the regular Bose-Hubbard model, because in mean field, once you get to here, you kind of have reduced the problem to a regular Bose-Hubbard problem. So
no, I understand the mechanics of the calculation, but normally when you truncate the system, you need a parameter to justify that the terms that you throw away are parametrically smaller than the terms that you keep. And I wonder what they are. The very fact that you have some kind of a closed, small region inside in the middle of your phase diagram tells you that by varying mu in t, you're not going to find a rationale for throwing away the other terms.
By other terms, do you mean like
when you started expanding around some expectation value, there's a way to do that is completely rigorous. You take the product, you put a number there,
right.
You write the operator is what you originally had minus the number. That's perfectly fine.
Right.
But if you do that, you're not going to get what you had, but they are higher order terms. And it seems to me that they are of the same order of magnitude as the terms you keep. That's not the case for small t or large t.
Mm-hmm.
So in the brownish and the bluish regions, you can.
Yeah, that's fair.
That's not the case.
Yeah. Okay. So you're saying, like, for example, just this this bare term here where I have these four operators is still going to be there, and
that's right.
Yeah.
That's
so
right.
That's totally correct. I mean, I don't think we have a way around that, and while those terms are still there, you kind of the kind of thought. Yeah. So I'm not going to attempt to justify this rigorously, which is kind of the reason for some of the numerical studies that will come later. But yeah, so I don't think I'm going to say anything that is totally satisfying. The kind of hope, the physical kind of guess here is that once you are in mean field and once you generate these single particle hopping terms, you can kind of ignore these larger these larger kind of nonlinear things. Even though this t is going to be larger, well, it's actually still numerically rather small in this region. But even if t is larger, the moment that you have these single particle hopping terms, they're kind of like dictating what goes on in terms of if you want to go into a new phase, when you start in the dipole condensate, if you want to go into a new phase, then where that happens is going to be, the physics of that transition into the new phase is kind of going to be dictated by these terms that are generated at mean field. So I'm not going to claim to be able to predict the exact shape of this phase boundary. That's something that requires, which may indeed be very hard to do analytically.
Okay. I also have another question. When you define your theta,
oh, theta back here. Oh, sorry, where was it? Here.
Here, right. So are these theta completely independent? So imagine we are in two spatial dimensions, so you have two thetas. Are they independent? Or is there a constraint if I go around the plaquette with these dipoles that would put a constraint on these thetas?
Yeah, so indeed, so there is, right? So I guess I don't have a good picture of this, right? But if you consider this like square, where I put bosons in kind of like a square and then daggers on the corners, right? Then you can interpret that kind of configuration as different kinds of dipole moments in different ways, right? I think I would say that, well, you can correct me if you think otherwise, but I think in the effective field theory, they're at least independent up to like, perhaps there are some subtleties that happen when you're thinking about kind of global issues. But if you ask, like, what is the central charge or something, like, how many massless degrees of freedom are there in this phase? The answer is that there are, the number of massless degrees of freedom is equal to the number of thetas. So I would say that they're independent from this kind of.
So let's multiply. Look at B dagger B around the plaquette. So you have B dagger B, B dagger B. So I can try and write them in terms of the thetas.
That's right. Yeah.
In terms of the end, because I'll have B dagger B at the same site.
Right. Yeah.
So there is a constraint relating the product of these e to the I theta with oriented product around the plaquette with the ends, which are roughly
So I agree. If you interpret this formula, if you interpret this formula literally, then just because this, like, a quadrupole can be decomposed in terms of dipoles in two different ways, right? Of course I agree with that, right? But in terms of this IR description, which is perhaps more of like a guess of what the IR theory is, that once you kind of abstract that this decomposing the quadrupole in two different ways is obviously true microscopically, but at least my current understanding is that when you look at when you go to this IR field theory, you're kind of treating each direction as independent, and they don't really become this like constraint that these different the constraint that these different dipole moments in the different directions are actually related to each other doesn't become apparent until you actually get into this phase where the kind of single bosons operators become allowed.
Well, I'm not even taking any limit. I just take the Hamiltonian and you describe it, and I try to rewrite it using these thetas. For any t, so not taking any limit or any assumption. I just rewrite it. So the change of variables from the B's to the thetas is not one-to-one.
Right, but I guess I would claim,
whatever it's called, that every configuration of B's corresponds to a configuration of theta, but not all configuration of thetas can ever be obtained.
Yes, that's correct.
So what is it? It's not onto or whatever.
Yeah, that's right. So I agree with that. However, I think that is, if you held yourself to a very high standard of rigor, then, and you try to do like a very careful derivation of something like this, then you would have to deal with these kinds of issues. However, yeah, I mean, it's going to be hard for me to justify something which is kind of wishy-washy hand waving things, right? But physical intuition is that in this phase, the different components of the dipole moment at long distances give you these effective fields. So yeah, I mean, I'm not gonna
maybe put this way, say it would be nice to having a additional, like we'll say, some global constraint on the theta parameters that one might investigate what might
We are not
qualitatively
talking about a
change.
global constraint. I'm not talking about a global constraint. I'm talking about the local constraint. The question I raised is not a question about the boundary conditions of the thetas or things like that. I'm raising. I think what Ethan said is perfectly acceptable. It's not rigorous. There's no parameter that justifies it, but we assume it's right, and then we continue. Which I take that as what he said, because the issue is not global. The issue is local. There's also, but that's secondary.
But can I say the equation right on there, degree of freedom is overcounting? Is that right? Is that what you're trying to?
That's right.
Yeah.
So you would, for example, say that partial x theta y should be equal to partial y theta x, something like that. And I'm claiming that constraint, you put that in at the lattice level. You say partial x theta y is equal to partial y theta x. That's true at the lattice level, and that becomes sort of manifestly true in this phase over here.
Mhm.
But the claim is that constraint kind of, you're putting in some Lagrange multiplier for that thing, and then you're doing mean field, and then that constraint gets kind of is not important in this phase. You can kind of sort of in this phase, the dipole objects, you can't really tell that they're dipoles, so you can't really tell that there's this partial x theta y equals partial y theta x in this phase. And you can only really tell that those objects are actually dipoles when you can actually see the single particles of which they're composed, which is in this phase.
It may be nice to see what might change if one do that analysis. I guess we can put that way. I don't know.
Yeah, I agree. Yeah.
But let me add something since we get here. I think take your time. In this phase diagram, you are trying to use two expectation value, the boson number B and also the dipole number D, whether it has a path, whether it's zero or non-zero, expectation value zero, non-zero, to label the three phases, correct?
That's right, yeah.
So my insulator is just B number is non-zero, right? And the D is D necessary zero, non-zero.
So my insulator, these guys are both zero. So these are objects which create dipoles or create bosons.
Sorry, I was saying
both zero, and then like this in this phase.
And the B how about the BEI? These are
let's go to that one.
B non-zero, D and non-zero. So I wonder, can we also use perhaps the dual degree of freedom? Let's say if I use the boson, the B, I possibly can find using the phase phi, I can write down the dual variable, the number.
Mm-hmm. Yeah, that duality B is something, right? So that duality is something which is, I mean, the way in which that duality works is depends on the dimension that you're in, right? You'll map to, say, a dual field in a dual scalar in one dimension. There's some kind of gauge theory in two dimensions, etc., like that. So that's something that you can do, and that's something which may or may not appear later in the talk. But yeah, you could approach things from that point of view.
So is that this part of that part of discussion clear? For example, right now, not just the dual variable for the phase phi of the B field. There is number for that, but there's also the dipole, and I suppose the vector symmetry, and maybe the dual variable is that the
so there's so for example, I guess there are many treatments of this that, well, I don't know about many, but there are some non-zero number of treatments of this in the literature. You can look, for example, at a paper just posted by Leo Radzahovsky, where he talks about doing this duality in terms of sort of two different fields, one for the dipole and one for the bosons.
Yeah. So let me ask one last question. Suppose we find a boson B field, and there's a phase for the B field is phi, and the dual variable for phi is m. Let me call MB, and for the dipole D, I suppose these are vector symmetry, maybe something slightly different. And however, I can consider the phase of the vector symmetry, and I dualize that, and there's the number for that maybe, and it's called n of D. My point here is that B, in terms of B and D, and maybe MB and ND, are there some relation between some of the variable have a VAF, then would they imply the other does not, or whether it can have both at VAF? Are there some kind of a constraint between them? Naively,
I mean, sure. Well, one kind of dumb thing is that if the B vev is non-zero, then the D vev is non-zero, for example, right?
Right, but I'm saying that in terms of a dual variable, I suppose the most naive way is that usually is, let's say, B VAF is B of there's also the EI phi, the phi gets some VAF. Then in that case, usually the dual variable does not get a VAF. And similarly, if N is get a VAF, the dual variable N get a VAF, then B does not. But I'm trying to say, because the phase diagram you have more complicated, is that possible there are some of the competing variable both get some VAF, or I don't know. I just ask in case you're sort of all the same.
Yeah, I mean, at least if you have two things which don't commute, then they usually don't both get vevs, right? So
okay. Yeah, maybe I can ask privately. Thanks.
Yeah, so that discussion might be most interesting in 2 dimensions.
Right. Well, another correction is that, right, in 1D, I think we don't have a superfluid, so I guess things about superfluid will change to algebraic quasi-long range. Is that right?
Well, yeah, it's in these dipole conserving systems, the story is a bit different, but yeah.
In 1+1.
Yeah, let me actually just talk about that. So why it's a bit different. So right. So this, in this phase, we have, as we were just discussing, we have both these expectation values in mean field are non-zero. And so here the single bosons can basically condense. They become gapless and they get an expectation value in mean field. And yeah, what's interesting conceptually about this phase is that while it has a Bose-Einstein condensate and the bosons are gapless, it's actually still insulating. So the conductivity vanishes, and it's not a superfluid, even though it's a BEC. And you can understand that by looking at this low energy action, which is something that many people, Nadi and collaborators in particular, have been studying recently. You have this kind of Lifshitz action here, where I have a usual kind of time derivative term here. Kappa is this compressibility. And then the derivative, for the spatial derivatives, I just have some extra spatial derivatives, which are a consequence of this dipole symmetry. So in this phase, you sort of the theta variables that we were talking about in this TC become the d of phi. So for example, theta x on the previous slide would become like dx of phi. And here, if my field phi is well defined, then here we definitely have dx theta y is equal to dy theta x, this problem we were talking about earlier. So in this phase, once I have this field phi, that's completely manifest. Whereas in the dipole condensate, sort of, if I were to insist on writing dx theta x as like dx phi, well, then this phi field would be governed by some non-local action. And so for the purposes of the IR theory, that's not really the appropriate thing to do. But in this phase, that constraint becomes manifest in the way that this field is realized. Okay, so this BEI kind of conceptually interesting because it separates Bose-Einstein condensates from superfluid, and that's what's in the rest of the phase diagram. Okay, so I think, yeah, maybe I don't want to take too long, but I'm gonna, well, we'll see how questions go. I'll just describe what we've been doing on the.
You have another
1 dimensional. Truman?
Another 30 minutes.
Yeah. Okay. Yeah. So I think an hour and a half long talk. I guess I was originally planning on not taking that long, but if people are interested, then of course we can go arbitrary long. But anyway, okay, so right, so as we were kind of talking about earlier, we drew this phase diagram within mean field theory, which is just sort of an educated guess, right? So in particular, we want to ask, for example, what happens in one dimension where fluctuations about mean field are strong. The expectation from theory is actually, it's not too hard to work out. You can use sort of bosonization techniques appropriately modified to take into account this extra conservation law. And you expect the following. So you expect that this dipole condensate, previously here, this dipole condensate was like a superfluid of dipoles. And you expect that in one dimension, this actually becomes a Luttinger liquid. So you have kind of power law correlations of everything, right? It's not, you don't have true long range order in the dipoles. You just have these power laws. Alpha is some kind of Luttinger parameter, some non-universal exponent, compact boson, usual compact boson story. Yeah,
so in high dimensions, do you think the usual superfluid can emerge at all in a system with conserved dipoles?
No, I don't think it can. The reason is sort of because this statement that I made earlier here about for example, the conductivity being 0. That's basically a symmetry statement coming from this dipole conservation. So yeah, this is going to be true no matter what situation you're in. The fact that the action for this BEI phase, this is kind of like what you get from the fluctuations about mean field. So this is what's going to hold true in large dimensions, bigger than 1. And you'll always have this extra derivative, and that's always going to sort of kill the superfluid stiffness. So you can think the superfluid stiffness would normally be the coefficient here. I have these 2 extra derivatives. So you can kind of think that the superfluid stiffness is suppressed by 2 powers of momentum. And in particular, it vanishes at 0 momentum. And that's kind of a symmetry statement. So it doesn't really depend on fluctuations.
I see. Thanks.
Yeah, no problem.
I have another kind of vague question. Hopefully you can help me make it more precise. So this dipole, the DC state, dipole condensate state, where the expectation value of D is non-zero, but of B is 0, I can view it as some composite order.
That's right, yeah.
People have been studying composite order for a long time, and we have many examples. For example, the spin nematic order is the composite order of the usual spin order. But apparently, if I want to make the analogy between spin nematic order versus the usual magnet, and here dipole condensate versus the usual Bose-Einstein condensate, there still seems to be some difference. And one source of the difference seems to come from the fact that here we do have another symmetry, which is the dipole conservation symmetry. But in the example of spin nematic order, the broken symmetry is still SO3 spin rotational symmetry. So suppose I want to look at this state within the context of composite orders. Is this maybe my question is in this context, is the dipole condensate phase special because it's related to another symmetry?
I think let me say yes for now. In the sense that you still have, I guess the sort of as I was just saying, like in the dipole condensate, you don't really realize that the objects that you're working with are dipoles necessarily. So if you just replace like dipole with charge, and you just think about this as like D different superfluids for dipole, right? If your charge is dipole instead of regular charge, then you can't really tell. So if you just are only in the dipole condensate phase where charge is gapped and charged objects are kind of very massive and can be ignored, then perhaps the fact that this symmetry is really a dipole symmetry is not important. So that difference may only manifest itself when you consider the fact that like you can drive a phase transition where, you know, these objects that you thought were fundamental are actually, you know, you realize that they're composite, and then things change across that transition. So you can, there are kind of ways of getting out of this phase which wouldn't be there if you didn't have this sort of extra symmetry, or if it wasn't really a dipole symmetry. But if you're just kind of deep within this dipole condensate phase, then perhaps there's not a big difference.
Mm.
Yeah, I don't.
Okay, thanks.
I'll let you know if I think of anything more intelligent.
I guess it's related to what you are going to talk now, but in the case of the usual insulator superfluid story, in 1+1D, the superfluid will be replaced by algebraic quasi-long range order. Maybe we can call algebraic superfluid. And there's no, the correlation function does not decay to a constant, but it's a power law decay in 1+1D. So how is the situation for the BEI in 1+1D? Is that something different than?
Yeah. So let's talk about the BEI. Actually, there strictly speaking, there is no BEI in 1D for the reason that I'll describe in this slide. So, yeah. So we just talked about how the dipole condensate should become this algebraic ordered thing, right? Just as Juven was just saying, for the same reasons. Becomes this algebraically ordered thing, no long range order. But actually also this BEI phase in 1D should theoretically disappear. And the reason for this is just that, you know, when we're in the BEI phase, we have this field phi, which is the phase of the boson. And this phi field is really only well defined in the absence of like vortices, right? If I have a vortex in the phase of phi, then, you know, that causes some point where this field phi is not well defined. And if I have a ton of vortices, you can imagine, you know, this action here where I just have these quadratic derivatives is not going to be appropriate. And in 1D, actually, yeah.
Sorry, it doesn't just mean that the vortices have to be in pairs.
What is it? Sorry, what does what mean?
You said that the field phi is not well defined.
Yeah.
Isn't that, you could have said the same thing for the Latinger?
Yeah, sorry. So I just mean that right. So yeah, let's for boundary conditions, let's always restrict to a net zero vortex charge, right? But if I have a large density of vortices, right? Of course, I can deal with isolated vortices. I can incorporate them to this framework. But if I have a ton of vortices, then this field phi is not really going to be this. You can still define this field phi in this way, right? But your low energy action is not going to look like this, right? Because phi is going to be totally disordered, and I'm going to have no right to do this like gradient expansion in phi, right? So this writing down this action and saying that this describes the physics of this phase is predicated on, you know, basically vortices not being being massive, essentially, not having proliferated.
Thank you.
Okay. So however, it turns out that dipole conservation kind of modifies the way in which modifies the ability of vortices to proliferate. So recall in a regular superfluid, if I have a phi as some vortex configuration, it looks like this on the right. You know, the winding of the phase, well, this like gradient of phi goes as 1/r, and I integrate over some region. This is in space-time, so they're really instantons, or in 1D, but I'm going to use the language of vortices. This integral, when you do it, diverges as the logarithm of capital R, where capital R is some IR cutoff to this vortex size. So this is a very large energy, and it kind of means that the regular sort of algebraic superfluid in 1D is stable for this reason. Vortices just cost a large amount of free energy, or a large amount of action. However, in this Bose-Einstein insulator, we have the kind of kinetic energy associated with the vortex, you have this extra derivative, and it renders this integral IR finite. So it doesn't, you don't have to put in some large distance cutoff here to make the energy finite. So basically, the energy of the vortex is just, you just have a core energy, and that's all. And that kind of means, you know, this is kind of a physical way of understanding something else, which is that when you write down, let me not go on. Yeah, when you write down some field theory, which is describing this Bose-Einstein condensate, sorry, Bose-Einstein insulator, in 1D, you see that the field theory always has relevant deformations. So you can always add these cosines to the theory, which create these vortices, and which are actually very relevant. They have like scaling dimension 0. They're like, they should just, and there's no reason for forbidding them in the action. And once they're present, they should just take off, and they should just totally kill this theory. Okay, so that was kind of the theoretical expectation, which we had when we went into doing some numerics, right? So the good thing about being in one dimension is that we can just check things with DMRG, right? And get an idea for what the phase diagram looks like. So I'll just briefly sketch what we find here. Let me point out that this phase diagram here, which is what we got in DMRG, is drawn at fixed filling. Previous phase diagrams were at fixed chemical potential. Sorry for that, but that's what was easiest to do numerically. We get some phase diagram that looks like this. So I'm not going to go over it in detail because there's something else I want to talk about, and my time is almost up. So let me just, however, say that what we find is, you know, we find Mott insulators and stuff in the places where they should be, and we find dipole condensates, this dipole condensate phase, at in some regions of where we expect the dipole condensate to be. But one thing that's kind of strange is that we actually find a phase, and this is in agreement with this earlier paper that I mentioned, who, you know, that reached conclusions similar to ours, but with maybe more high-powered numerics. We find that there's this BEI phase seems to be remarkably stable at non-integer fillings. So like just at some random point over here, we find that it seems like you get a BEI even though you have this expectation from theory that it shouldn't be true. So we have this kind of weird situation where you know, our DMRG is perhaps not capturing the thermodynamic limit very well, but it's rather strange because we're, you know, from a field theory point of view, we have a theory where there exists these relevant operators with scaling dimension 0 that should be in the action, and somehow they're just not showing up really at all at fractional fillings, which is kind of like every field theory person's nightmare, right? So normally you think that if I have a very relevant perturbation, doesn't matter how small its bare term is, the bare coupling constant for that perturbation is, you know, it's just going to grow.
Can you explain again which term is missing?
Yeah. So sorry, I didn't write this down on my slides, but it's the term which creates vortices. So in one dimension, you can do a duality in terms of the theta fields, which are, sorry, not the theta from the earlier slides with the dipole condensate, but the field which is kind of dual to this phi. And you should add cosines in that field, and you should also add like cosines in the derivative of that field and stuff like that. And there are these cosines of this dual field which are very relevant at the BEI fixed point, but for some reason don't seem to be showing up very strongly in the numeric. So it's a bit of a mystery. But yeah, cosines once you do duality, you have cosines, and it's those cosines.
Well,
yeah.
So what's your explanation for this fact?
Oh, we don't have an explanation. So we're trying to.
Let me make sure I follow. So you're saying that term, the BEI phase, the instanton, they have a finite energy, then they can be populated, created, and then that will destroy the BEI phase, right? That's what you say. So, but that's predicted by field theory, but it's not seen in numerics. That means there is some suppression on that effect, and you don't know how to get that suppression.
So what exactly we see is that when I work at integer fillings, so like along just this line here at filling 2, the field theory seems to work completely fine, and you don't have any of this BI phase. You only have this dipole condensate, and it seems like the vortices that kill the BI condense, that's totally fine. At fractional fillings, the operators which create vortices are slightly more complicated because in order to preserve translation invariance, you need to add. You can't just create single vortices. You have to create like multiple vortices at the same time. So instead of cosine of theta, you have to do like cosine of 2 theta at half filling, something like that. And it's at these fractional fillings where we just with this Hamiltonian that we just put in this dipole Bose-Hubbard model Hamiltonian, somehow they're just not showing up very strongly in numerics. So this kind of maybe a little bit of a mystery that we haven't solved yet.
So what's the scaling dimension of cosine 2 theta supposed to be?
Yeah, okay, so I really should have had a slide with the equations here. So the scaling dimension of the operators is actually 0, that we're thinking about being relevant. So it's essentially like the action that we have for the dual model, for the dual variables, looks like exactly like this, except I just replaced phi with its dual. And then the operators which we're worried about would look like cosine of the derivative of the dual variables. So like cosine of partial x theta. And then the free fixed point is just, I replace these phi's with theta. And basically, if you work out what that operator is, that operator just has correlation functions which are a constant at long distances. It has scaling dimension 0. And by all rights, that should just be very relevant. So somehow it seems to not be showing up in the numerics.
Yeah. Is this DMRG infinite DMRG or finite DMRG?
Both. Yeah, we did both. Yeah.
I see.
Yeah. So
I'm still puzzled by this question of the operator that is missing. So it means that some link in the reasoning is wrong, right?
So
the way you say it, either the numerical is wrong, or the field theory is wrong, or the argument that this operator should be there is wrong.
Yeah, so I think right now we are feeling is that these when you take the literal, so for DMRG we have to input Hamiltonian, right? So we input this exact Hamiltonian, and we just have this on-site repulsive interaction, and we just do that Hamiltonian, right? I think our current feeling is that for some reason the bare coefficients of these terms which create these high vortices are just like incredibly small for some reason, or this DMRG algorithm is not exactly capturing, like, I mean, it's not really doing RG flow, right? You're doing some variational analysis of energy, so you're not really doing, anyway, it's just not exactly capturing that. What is more would be more, well, what is more worrying, but would also be more interesting if there's some actual reason why these vortex operators can't appear in the action. We haven't really thought of any reason why they shouldn't be there. So there's a possibility that some line in some argument in the field theory analysis is wrong, but neither us nor this these folks have been able to reach a conclusion on that. So yeah. So maybe stay tuned. Hopefully this will be figured out. But yeah.
But something here will have to give, right?
Okay. What's that?
Something in this logic will have to give, because the way you presented it, there's a real contradiction.
Yeah. So the question is whether what gives is just you have to kind of on the numerics, right? So we're not actually getting the thermodynamic limit in the numerics, or there's some weird accident of this Hamiltonian. Either that gives, or our theory gives. So I think I lean more towards there being some subtlety with some like accident with the numeric. So what we're doing right now is just adding a bunch of random crap to this Hamiltonian to see if that changes the story. Right? There's some accident with this Hamiltonian, but we don't know yet. So
and that occurs only in 1+1 dimensions, or in all dimensions?
That's only in 1+1 dimensions. So in 2+1 dimensions and higher, this BEI should be stable.
Did you do numerics for 2+1D? 2D?
Yeah, so that requires quantum Monte Carlo, and there's one of our postdocs, Byung-min, has been working on that a bit, but we don't have any results yet.
Do you see BEI already on?
No, we don't have any results, so we don't know yet. But I expect that you should have a BI. Yeah, so there are also some things here, like there are some phase transitions here that seem to be kind of interesting. If this BI really does exist for some reason in the in this phase, then it's kind of interesting, because some of the phase transitions that occur in one dimension we actually couldn't figure out, despite the fact that it's just a 1D model. So there's maybe some interesting things left to be addressed here. But anyway, this is the current state of affairs. And I'm just gonna, since I don't have much time left, I just want to quickly talk about this last part of the story, which I find kind of interesting and is a little bit of a different flavor. And this is going to be work that will appear probably this year, maybe too optimistic. So yeah, I'll just briefly describe what happens. In this phase diagram here, I have this green region that I haven't talked about, before in the talk, but this is kind of the phase that you realize in this region is actually something that all dipole conserving boson models are going to share. And it's kind of an interesting type of instability occurs in this region, which is actually very simple to understand. So, recall the important fact that when you take a boson operator and you act on a state with n particles, well, the boson operator reduces the number of particles, but you also get this factor of square root of n, right? Okay, this factor of square root of n is very important because it means that when you act on a state with n kind of density, average density n, this psi n here, with an operator that hops these a dipole hopping operator, the dipole kinetic energy term, each of these boson operators sort of schematically scales as square root of n. So this whole thing, sort of has in some rough way has a size which is proportional to n squared, right? What this means is that, very much unlike the usual story, here both the kinetic energy term and the potential energy term scale with the particle number in the same way. So they both scale as n squared, right? In terms of their strengths when acting on the state. And so in particular, if I make this T bigger than U, or comparable or bigger than U, well, this is going to become negative, right? And when that happens, energetically, what I want to do is I want to just make n as big as possible, right? Because I can lower the energy in this, at least within the context of this simple model, I can lower the energy arbitrarily just by making n as large as possible, right? This is very different from the normal Bose-Hubbard model, but it's kind of an inevitable consequence of this dipole conservation, because dipole conservation means that you only have these quartic operators. And indeed, when you do DMRG in this regime, you see just all the bosons go into one big clump, right? This is the ground state that DMRG found. So that sounds kind of boring because, okay, you just form one gigantic droplet. Not so interesting, but that actually is not going to, my claim is that actually is not going to occur in a real system. And you can realize that as follows. So suppose we start from some uniform density state. So this line here represents a density as a function of space. And suppose we want to make one gigantic droplet where I put all the bosons in the center, right? So that, as we just said, that's what's favorable energetically. But that can't really happen, right? Because if I want to make a big droplet in the center, I can't just start moving bosons from the left into the center and moving them from the right into the center because of the dipole constraint, right? Which means that bosons can only move in a coordinated way. So I would have to take a boson at the left of the system and at the right of the system and have them hop towards the center at the same time, right? Simultaneously. They have to coordinate their action with each other. But when the system is very big, that's going to be impossible, right? So what happens instead is that, you know, you'll start forming some try to form some droplets here where the density increases. And then I'll try to make this droplet bigger, but you're going to be frustrated from dipole conservation, right? So I say I want to make this droplet bigger and I want to push it into the center of the system. Well, dipole conservation says if I try to move charge to the right, I have to move an equal amount of charge to the left, right? And then that kind of, I tried to draw that here. Unfortunately, there are many Fourier modes to these lines, so it's kind of hard to draw. But as I start trying to move charge to the right, I have to take charge away from the left, and I just kind of end up with this this kind of like wavy structure, right? So anyway, TLDR is I can't move all the charge to the right. I have to do this compensating process, and it leads to these kind of sort of multiple different droplets that form. So to illustrate all of that reasoning in a movie, here's what it kind of looks like. So this is some I've kind of this movie is generated with some dipole conserving Markov circuit kind of deal, but this to give you a flavor of what happens. I've done a quench from an initially uniform density. I guess here the average density of bosons is maybe 5 per site. And you see that what happens is that even though all the bosons want to go into one big clump, they kind of get stuck and they form these like clusters. And yeah, this kind of gives you a very weird form of glassy state where the system doesn't really thermalize, but it's kind of a weird type of glass because you have these gigantic clumps of bosons, and each clump of bosons is this very like quantum mechanical object. So it's kind of a strange phase. Yeah, let me skip this. We've done some other types of simulations to verify that this happens. And then I'll just close by saying that this phenomenon here, this dynamical phenomenon, actually seems to already have been observed in experiment. As an example, there's an experiment by Martin Zweierlein's lab at MIT where they saw a Bose condensate, a quasi one-dimensional Bose condensate in a magnetic field, which, as we discussed earlier with this quantum Hall thing, kind of gives you a dipole conserving system. They saw that the system, when you just let it evolve in time, fractures into these kind of spinning tornado-like objects, and it does so. Our claim is that it does so for just for this physics, the physics responsible for this kind of fracturing. So this kind of physics occurs as long as t is kind of bigger or approximately equal to u over in this side of the phase diagram. And so this is kind of a universal thing that happens for these dipole conserving models. Okay.
Sorry.
Cool. So
excuse me. How do you do the animation simulation by which governing equation?
Yeah. So this is this simulation is a heuristic. This simulation was generated just by taking a classical model of particles where the particles hop in a dipole conserving way, and just doing sort of infinite temperature Markov process on this. So you just like basically randomly do dipole conserving hops of these particles, right? So this was initialized at a totally uniform state. The first frame of the animation has already been like 100 steps or whatever. But you start from some initial state and you just randomly do these dipole conserving hops, and the system just kind of spontaneously forms these clumps. Getting more serious, you can do sort of TEBD. So you literally just run e to the minus IHT on a superfluid, like an initially uniform density state. and you see that this also happens. So I mean, there are bajillion different numerical tools that you can use to kind of see that this behavior occurs. Yeah. Okay, so that's it. What are some more things to do? Well, as we kind of discussed, there are some maybe some lingering unresolved things in one dimension. More generally, you have dipole symmetry plus something, where that something can be fermions, right? These phase diagrams are going to change for fermions, SPTs. I mentioned that there's some quantum Monte Carlo work being done on the higher dimensional model. I would be also very interested in, experiments. Some of the stuff that I alluded to earlier, it's clear that this is something which is very feasible. And, okay, more generally on the theory side, right? Let's just you can think about understanding the quantum ground states of systems where you have some kind of kinetic constraint. So be that dipole conservation, maybe quadrupole moment conservation, whatever, or something that is perhaps maybe less obviously associated with a symmetry, right? There are kind of various prescriptions for writing down models where the motion of particles is constrained in some way, and people have mostly been thinking about these from the point of view of quantum dynamics, but are there interesting things to be learned there in terms of sort of the low energy or the ground state properties of the systems? That's something also to explore. Okay, so stop there. Thanks everyone for sticking around.
Thank you, Ethan. Very nice seminar. Thank you.
No problem.
Question from the audience?
Yeah, I guess I had a question. Could you have, do you have an idea how you would modify your dipolar Bose-Hubbard model so you would only condense n dipoles instead of condensing, one dipole pair?
N dipoles instead of one dipole.
Yeah, or another way to phrase it is just spontaneously breaking the U1 dipole symmetry down to a ZN subgroup instead of completely breaking.
Yeah, that's an interesting question, which I haven't thought about. Let me think if that would be natural. Yeah, sure. Yeah, I don't know exactly what the property of that, the gauge theory that you would get, what that exactly would look like, and if, for example, if you then tried to condense particles on top of that state, yeah, that's kind of interesting. I guess that kind of relates to the stuff that you were working on. You would have some effective state where you're breaking dipole only mod some integer, right? And then then you have a lot of the physics of stuff you were doing.
Yeah, I think I understand I feel like I understand the phase that you get, but if you handed me your dipolar Bose-Hubbard model, I don't know what I would do to only condense n of them. I understand the symmetry breaking pattern. I can just write down a model that realizes that symmetry broken phase, but I actually don't know how I would get that model starting from your. It's you have a U1 theory, and that's the parent of the ZN theories, but I actually don't know how to have the parent and the child meet.
Right. Yeah. So, usually, you can think about the same thing about so maybe first you can answer that question for just regular superfluids, right? So of course I have a system of bosons. I can condense single bosons. I can also condense 5, 6, whatever bosons. I actually don't know of any examples where condensation of these composite objects of bosons is something natural. I have no idea how you would engineer a Hamiltonian that does that. And since there's just within this model, there's no symmetry reason to distinguish. There's no other symmetry which is carried by the bosons that would change the quantum number of a bound state. That might require some kind of tricky tuning of various parameters. But perhaps in a system where you have some other symmetry, it could be more natural. I don't know. It would be good to think about.
Okay, thanks.
I think a natural way to do it is just to add to the Hamiltonian big term proportional to the hopping of that object to be condensed.
Uh-huh. You mean like the hopping to the some power of the hopping or something?
Hopping of dipole to some power dipole.
Yeah, to some other power. Sure.
Yeah, the same power. It's supposed to be a hopping of the object to be condensed with a big coefficient.
Yeah, I mean the worry is that like, well, yeah, maybe, I mean, is if there's no reason for forbidding the single dipole hopping, right? Would the single dipole hopping always be like more, I guess maybe it wouldn't be more relevant. Perhaps they have the same.
I don't know, it's hard to say that. In models, spin limmatic can be realized instead of spin order.
Uh-huh. Right, and so that's a higher order operator. That's right. Yeah. Okay, yeah, so that's a good suggestion. Yeah.
Please, could you comment a little bit more about dipole symmetry in fermionic systems?
Yeah, so yeah, so there are a few. So the kind of Hamiltonian that you would write down, I'll scroll back a ways, is exactly this kind of Hamiltonian, except well, these are going to be replaced by fermion operators. I have a b squared here, so I'm not going to be able to do that with fermions. I think the most interesting things are going to happen when those fermions have spin. So you have to write down some appropriate model like this. I think the one that we've been studying is the one that you get from a tilted optical lattice, because we're kind of have that as an experimental motivation. And there, yeah, you have some kind of dipole conserving fermion model, and there you put the spins in here in some appropriate way. Yeah, why you might expect that this fermion version to be interesting is, for example, we have this phase diagram. Well, what should the analogous phase diagram for fermions look like, right? Or in particular, like what's the analog of this BEI phase, right? Well, sort of in this phase, you had, the bosons are trying to do what they would normally do at strong hopping, which is to form a superfluid. But then the dipole conservation comes in and modifies how that works. For fermions, well, the thing that fermions like to do when there are large hoppings, or really any hopping, is to form a Fermi liquid, right? But so that at the mean field level, once you've condensed these dipoles or whatever, the fermions will try to form some Fermi liquid. But there's this kind of general thing about these dipole conserving systems, is that they're insulating. That's kind of a symmetry reason why they're insulating. So if you try to form a Fermi liquid, you might get something with a Fermi surface, but you're going to have something which is insulating, right? So the fermion models are interesting in the sense that you can kind of explore what is this, may give you this very simple realization of an insulating system with a Fermi surface. Yeah, and then you can also explore like how various types of spin order interplay with this dipole conservation and things like that. So I think there's some, I think that it'll we kind of have some stuff in that direction going on, and I think that'll be kind of good. Well, we'll see how it goes. Yeah.
Okay, thank you.
Yeah, Juven?
Let me ask, can you say more about the experimental data? I think just
This or
yeah, what we look at. I think you have 2 or 3 figures that you show
earlier, right?
Yeah, actually those one are good. No. Just the last few about the
refractory.
Yeah, that one. The real-time dynamics, this one, and also this two to the D3. What?
Yeah. You just want me to say what this actually is?
Yeah.
Yeah. So the top one is what people have done here is they've taken a bunch of bosons in a optical lattice, which is kind of 2-dimensional. Basically, they're optical lattice. The bosons in their system form a bunch of like tubes. So they're kind of localized in 2 directions and extended along the third. And the lattice is tilted in a way which gives you dipole conservation along one of the directions. And what they did is they just loaded a whole bunch of bosons. So here the boson number is very, very high. They have tons of bosons, and they do this tilt, and they basically do this quench from as uniform of a state as they can get. And you can see that they kind of have these like spontaneous pattern, these kind of density waves that are occurring, right? And this is occurring despite the fact that the bosons are, completely short range interacting, right? So this sort of charge density wave that you get here is not because the bosons are like repelling each other, right? And they're trying to, there's no like, nearest neighbor repulsion. It's just a consequence of this dipole stuff that was responsible for this movie. That's this experiment.
By the way, the dipole here is respect to a mean density, like non-zero, or the respect to zero? Because here everything is non-zero, right? So
yeah, so you
it
doesn't. Yeah, so strictly speaking, dipole moment is not really well defined when you have non-zero charge, right? That doesn't really matter. The important part of dipole symmetry, well, this dipole thing is just that there's this like local conservation law. So things like that are not so important. But yeah, they basically have this kind of thing. Yeah, you'll see that the on-site population here of the bosons is gigantic, right? So, we've been thinking about filling fractions of order 1. Here they have like hundreds of bosons on a site, right? But it's the same principle is operative in this experiment. And then this one, so we've been talking with Zarilan's group a little bit about trying to basically use our 1D dipole model to make some predictions for their system, but they basically have they have a spinning Bose-Einstein condensate. So the spinning creates this magnetic field. So you basically get bosons in the lowest Snyder level. And they also kind of put in some trapping potential initially to prepare the bosons in a line, pretty narrow strip. It's kind of a 1D system. And they let it go, and it does what you see in the figure. And even though this is in 2 dimensions, in the sense that these droplets have some structure, you have these nice like spiral galaxy shapes, right? All this structure is really sort of can be projected onto a dipole conserving 1D model, and by analyzing the dynamics of this one-dimensional dipole model, you can kind of like project it back up into 2 dimensions and see how all this like this dance of these vortices or dance of these droplets is occurring in the 1D model. So yeah, that's that experiment.
But the dipole conservation is also due to the tilted optical lattice here.
The dipole conservation is due to the spinning, which creates this effective magnetic field, right? So remember we were talking about the quantum Hall effect and how in the quantum Hall effect, momentum conservation in one direction is equivalent to dipole moment conservation in the other one. So in this system, once they kind of turn off the potential which traps the bosons in this line, they have translation invariance in this direction, the horizontal direction. And that translates to dipole conservation in the vertical direction. So you should think of this as being described by a 1D dipole conserving model where you have like a bunch of lattice sites which are running along the vertical direction of this figure.
What's the highlighted this caption? Was this a black cross in this region?
These crosses are vertices so you basically have droplets of kind of like a kind of like a real space Bose condensate sort of. So you have these droplets of a bunch of localized bosons, and they're separated by these black crosses, which are vortices that they're able to image. So you should just think basically in this 1D model, you have these clumps of bosons and these voids, and the voids really, when you map them to kind of map them back up into the 2D problem, kind of take the form of these vortices that they image here.
Okay, thanks.
Yeah, no problem.
Any other comments, question?
So can I maybe ask a rather vague question, because you mentioned SPTs with dipole
Oh,
symmetry
yeah, sure.
there? Yeah.
Huh?
So what I know is that dipole symmetry kind of shows up in like lattice systems with subsystem symmetry.
Yeah.
So in this case, let's say I have SPTs that have subsystem symmetry, and then I can construct like a higher order kind of like a classification with higher degree group cohomology class.
Right.
Yeah, so that's kind of the idea. But would you expect like dipole symmetry with like SPTs with dipole symmetry? Would you expect like the classification to be just that, like H3 or something?
I'm not. I don't know. Yeah, that's a good question. I think I'm not sure if going to the full subsystem symmetry is maybe a bit overkill, because you're introducing sort of an infinite number of conservation laws, and here I'm kind of interested in, you know, the kinds of symmetry protected phases that you can have when you only have what you know, an infinitely small subset of the full subsystem symmetry, right?
Right. Yeah.
So actually, to be totally honest, the like mathematical classification in terms of what cohomology groups should I calculate, that kind of thing, I haven't thought too much about. Really what we've done so far is to just, you know, come up with some simple models in 1D which have dipole symmetry and which are SPTs, and to just kind of study them directly. So I think it would be interesting to think about the kind of the full theoretical framework. It's interesting to me because, well, I think this is something that people understand, but not me, which is like, you know, SPTs. I often think of them in terms of response theory and you know, and when you have dipole, it's like, yeah, gauging dipole is like, you can kind of, well, at least it's easy for me to get confused when I start thinking about the relation between dipole and then the global charge and like how the gauge fields couple to each other.
Right. Yeah, it's subtle. Yeah.
Yeah. Luckily, I've been having some conversations with Hotat Lem, and he's
okay. Good.
So I have an unfair advantage because I have access to Hotat. So we'll try.
Okay, yeah, it's a very interesting question. I'm looking forward to the direction that we will go. Yeah.
Cool. Great. Thanks.
Thank you.
Okay. Thank you, Ethan. I think it's about the time.
Thank you.
Very much.
Nice talk.
Thanks, everyone.